looks like we have life, and the pen might be working now. I think that's what it took, was to completely unplug the computer and reattach it. Well, I didn't have time. I barely had time now. I'm late. I'm 4 minutes late. Okay. So, apologies for the delay, but technical difficulties. You understand. Let me get that started and get back to the announcement. I think it's fixed. I think it's fixed. There we go. Okay. All right. Finally, back into the swing of things. Okay, so a couple things. I actually assigned homework 5 on Monday, and it's been on Blackboard. I've got hard copies today. So 1, 2, 3, 4, 5, 6. Or homework 9, sorry. That's what happens when you're running back and forth. 1, 2, 3, 4. What? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. Later. I'm gonna lose them. There's a chance I might do a quick re-recording of Steel, considering everything that happened. I'll just do a quick little blurb and add it. I just said that. I know. Well, see, you messed everything up. You know, you messed my equilibrium up. Okay, all right, everybody settle down. All right, homework 9 is due on Friday, so again, I mean, you all can do what you want, but I would not wait until Thursday night, especially you that are in, the folks that are in Steel. What? Okay, we're dialing the mistake counter back on that one. Oh, no. What are you going to, like, turn in a golf ball with your homework? You know how, like, when they shake the principal's hand, you have, like, a golf ball in your hand? You've never heard that? Okay, somebody's heard that.
Not a golf ball, but, like, something else.
Yeah.
Stickers. After we got our diplomas, we patted our principal on the back.
Oh, is that what you did? All right. Okay, so real quick, before we get into columns, I'm sure you all are starting to get the emails about course evals. If you notice on Blackboard, what I've done is I've created a course eval column. If you provide me proof that you have done them, I will give you bonus points on your homework average. Just do me a favor, and all you have to do, you can walk up to me with your phone and say, here, I've completed it, or you can send me a screen capture of your completed survey list, and I'll add it to the grade book. So. His words, not mine. All right. Does anybody have any questions as to the schedule? Your last homework's due Friday. I'm not accepting late homework because I'm giving you all the solution. We have exam review that day, and then we have our exam on Monday, May the 1st, starting at 10:15 a.m. for 2 hours in here. Doesn't matter. We're doing it. Yes. I'm staying out of it. All right. So today, all right, settle down. All right, so what we've done for the past couple lectures is talk about column analysis, particularly how to determine VPN for square columns and for circular columns. Now we're going to get into design. And I believe we have already discussed the design procedures for columns. It's pretty straightforward. I want to get into this again. All right. So, okay, all right. This is really important because I guarantee you, I'm going to say this. I'm going to use my words and say it. I guarantee you there's going to be folks on the exam who's, oh, yeah, I wasn't paying attention, so I'm just going to do this. You want to pay attention to this. Okay, so when you design a column, the first thing you're going to do once you determine your axial load is you're going to solve for the gross area. Now, in order to solve for the gross area, you have got to guess a reinforcement ratio. Unless otherwise stated, 0.02 is a pretty good place to start. You solve for your required gross area. You do not take your designed column and just multiply it by 0.02 to get your steel. That's not how it works, okay? Once you have a gross area for your column, you can directly solve for how much steel you need. Sometimes it may be more than the 0.002 or 0.02. Sometimes it may be less than 0.02. The idea of the 0.02 is to just get the column size. Once you get the column size, you can then solve for how much steel you need. Okay? Make sense? Now, if typically you want to round column dimensions to the nearest inch, maybe the nearest 2 inches, 18 inches, 12 inches, 6, something like that. There is nothing wrong, I want to be clear, there's nothing wrong with doing a calculation and getting a column size of, let's say you need a dimension of 18.3. There's nothing wrong with saying, well, I'll just round that down and use 18, because what you're then going to do is take that real column size and determine how much steel you need. So the idea is this. Let's say you use 0.02 to get a column size. And let's say you do the math and the dimension needs to be 18.3. If you round that dimension down to 18, that's fine. That means you'll need a little bit more steel to make up for that. Does that make sense? If you take that 18-inch column and multiply just by 0.02, you will end up getting less steel than you need, and you'll have an unsafe column. Does that make sense? That's why you can't just take this and multiply it by 0.02 to get a layer of steel. Sound good? Yes?
Might be a stupid question, but would it be more conservative to round down to 18 or round up to 20?
Well, it doesn't matter as long as you're using, see, let me answer it this way. So you use your reinforcement ratio to get your minimum gross area and use that to select a column dimension. Once you've got the column dimension that you want to go with, you take that column, plug it into this to solve for the required amount of steel. So you're asking, is it more or less conservative? I'd say it really doesn't matter, because ultimately you're going to use the actual column dimensions to solve for how much steel you need. Does that make sense?
So then your reinforcement ratio will be different from what you originally.
Exactly right. Exactly right. And that's another way of explaining why you can't use the 0.02, is that ultimately your reinforcement ratio at the end will be different. Although that's the case with just about every beam we've ever designed. I mean, you use a reinforcement ratio to get a steel or a level of steel, however much area you need, and then you always end up picking a little bit more, so it does change a little bit. But I do see what you're saying, and that is another way of looking at it. Sound good? Okay. So we're going to design a square column, and then we're going to design a spiral column, or a round spiral column. So design a square tied column to support an axial dead load of 130 kips and an axial live load of 180 kips. Okay, so we're going to begin using a row value of 0.02, 4 KSI concrete, 60 KSI steel, and then we'll go to work from there. Okay, so let me turn to that. Well, here, let me open up my notebook, and then we'll turn to that. We're here. Okay. There. Now everything's working. Okay. So, example 19A. So first thing, we know that FC prime is 4 KSI. We know that Fy is 60 KSI. We know that our rho G, we're going to take that to be about 0.02, which basically just means that's the starting value for the purposes of design. Bless you. And then we've got a dead load of 130 kips and a live load of 180. Goodness. So somebody help me out. What's the first step? Factored loads. Bless you. It's that time, isn't it? Seasons change, and that brings the allergies. So, 1.2 dead plus 1.6 live, 1.2 times 130 plus 1.6 times 180 yields what response, or what answer? 444. All right. Now we are using tied columns, so essentially we're going to use a square column. All right. So what does that mean for our safety factor and our eccentricity factor? Got to go through your notes. Oh no. The what? 0.8, and the phi value? There we go. All right, sound good? Now, what the first thing that we are going to do is we are going to solve for a required gross area. And we're going to solve for that as follows. So, AG min equals, we good? Okay. Phi alpha times the quantity 0.85 FC prime, 1 minus rho, and then plus Fy rho, and then all that under PU. Okay, so 0.65, 0.8, 0.85, 4 KSI, and then what I'm going to do is I'm going to say 0.98. Everybody see what I'm doing there? 1 minus rho. Now, how many of you are actually writing the KSI? Make sure, again, write those units out. Not me, you got to worry about. It's NCEES. They're the ones who issue the FE exam. So what do we get for this? There we go. Is there a second on that 188.4? I heard some discussion over a 188.5. All right, okay. All right. Okay, all right. Help me out with some basic geometry. What was the shape of this column again? Okay, now if this area is 188.4 square inches, how am I going to determine what size column is necessary, or what are the dimensions of that column? You all are really excited about exponents. All right, guys, everybody, come on. Everybody, tighten it up a little bit. Come on now. 13.73 inches. Relax a little bit. It'll be all right. 13.73 inches. Do I have a second on that? All right. Now, typically, when you're in column design mode, you're usually wanting to round to the nearest inch. And because of the ease of forms and pre-made forms and things like that, I usually like to keep it to the nearest even inch, like 16 inches, 18 inches, something like that. So if this is my minimum required column dimension, again, based on an assumed reinforcement ratio, what would you use? There we go. So let's use a 14 by 14 column. You could, but I think that would make form work ultimately a little more complicated. To be honest, you could go with 12 by 12 if you wanted, but the amount of required reinforcement would just get larger. You see what I mean? So let's use a 14 by 14 column, and then that's going to mean our gross area is what? 196
inches square.
There we go. Yes, you could. You're exactly right. If the architect says, sorry, can't be larger than 12 inches, well, then you could just use a 12-inch column and determine how much steel you need. But let's also extend that a little bit. Let's say that the architect says, must be 12 inches by 12 inches. And you do the math, and you find that you need so much steel that it exceeds 8%. You call the architect and you say, sorry, isn't going to happen, so. It's an option. That's an option. Now, to get the required amount of steel, I'm going to move on to another slide. Does everybody have all this? Okay. All right. To get the required amount of steel, you do not take that column and multiply it by 0.02. See, that would be an overestimate of the required amount of steel. Why would it be an overestimate? Exactly. The column got bigger, so you shouldn't need as much steel. That's sort of the whole point. So,
and what happens if you have too much steel? Why is it such a bad?
You need enough concrete at least to develop that reinforcement. You see what I mean? Your reinforcement ratio can't get too high, or you're not able to develop the reinforcement that you've got. You see what I mean? That's for columns. For beams, if you put too much reinforcement in it, what happens? Well, you over-reinforce the section, you demand more capacity out of the concrete, and when it fails quick. Remember that? behavior. Awesome stuff. Now, what? I don't know what's going on. The personification of steel and concrete. I'm just going to write my equation. Okay. All right, so here's your equation for solving for the required amount of steel. Again, it's just VPN has to be greater than or equal to PU, solving for the steel. That's all that is. It's nothing really that complicated. So plug and chug, we got 444 kips minus 0.65, 0.8, 0.85, 4 KSI, 196. Now again, we're not using what we solved for, we're using the updated column dimensions.
Your alphas look like subscript A's.
I was like, where is B? Oh, it's not a B.
Yes, fish.
You know, y'all are hurting my feeling with my handwriting. I've already dealt with that with other classes. Yeah, I'm sure you don't. Please. All right, hold on. I don't even know what I was doing. 60 KSI minus 0.85. All right, settle down, everybody. Settle down. Let's calm down a little bit. I know this stuff is exciting, but goodness. What was that? Yeah. What do we got? Say it again. 3.31 inches squared. Oh, goodness. Had a cord tangled. Okay, so help me out. Okay, we need to select a reinforcement pattern that goes along with this. So you can actually go back to your beam design chart. Everybody, let's go find that beam design chart. Hold on. Let me borrow your notebook real quick. Y'all remember this? Well, look. Okay. Now, in terms of looking for a reinforcement pattern, okay, let me see this real quick. So, okay, let's keep in mind that this is a column. So would 7 bars really make sense for a column?
17 number 4. I'd go with 4 number 9s.
Okay, we got 4 number 9s. What's the area of that?
4.
Okay, is there another option? Okay, hold on for 1 second. What did you say? Okay, 3 number 10s. Again, going back, keep in mind this is a column. We're not lumping the reinforcement all onto one side. We want to spread it around. So how would you evenly spread 3 bars around a square? I'm making a point. I'm really trying to make that point. That's important. Somebody said something else. 8 number 6s. Now, what's the area for the 4 number 9s? And what's the area for that?
3.53.
I'm going to go with that.
I want 17 number 4s. Yeah, Joey, you're wrong. 11 number 5. You could put 1 in 7.
Now, what was that? What was the area?
3.53.
All right. Goodness gracious. My goodness. I'm having a day.
So what they do, tie three of them bars together and put them into square?
What?
Four, what they say?
We had 8 on the last example.
You put it in the middle. It's on the inside, dude. Put one on each corner and then split the difference.
Okay, let's just remember that 6-inch spacing requirement? Remember that? All right. Let me ask you a question. We're not done with this column design because there's a number of details that we need to assess. What tie selection we're going to use? What's the tie size going to be? Why a number 3? No, there's a reason for that. There we go. Longitudinal bars. Well, that was a correct guess. All right, settle down. Goodness. Yes. Guys. Okay. Now let me ask you this. If you're in design mode, okay, and you want to design a column, you're trying to design the most economical column that you can. Let me ask you a question. When sizing that column and spacing out this reinforcement, let's talk about the tie reinforcement. Are you wanting to use maximum tie spacing or minimum tie spacing? Why are you wanting to use maximum? Exactly right. So let's use maximum tie spacing. What is the maximum tie spacing that we can use? What is the maximum tie spacing we can use? No, that's the minimum. All right, let's take it one at a time. Mr. Schaffer, what's the first one?
48 tie bar diameter.
So what is that? 48 times what? 3/8. So what is 48 times 3/8? What's the next one? Somebody else. Somebody other than Mr. Schaffer. What's the next one? 16 longitudinal bar diameters. Which is 16 times what? It's a number 6. So what's the diameter of a number 6? 6/8. What's 12? And what's the least column dimension? So I suggest that we use number 3 ties at 12 inches. Got to go off the minimum. So I propose that our column should look like this. Bless you. All right. So, what do you think we ought to use for a cover? Unless otherwise stated, that's a good one. And there's your answer. However, there's two things we need to check. We know that our tie spacing works. We selected our tie spacing based off of the requirements. We've got two things left that we need to check. The first thing that we technically need to check is row actual. So that is AST over AG, which is, what was the area of the steel that we actually picked? Divided by 196. What do we get? Now, there's no units on this, so. .018. Is that a good response? Yeah, because it's got to be between .01 and .08. And we should check this. I mean, let's be clear. We used .02 for a starting design, but we changed our column size and changed and picked a different rebar set. So, you know, you got to make sure that what you're doing makes sense. So this is a good check to make in the end. The last thing we need to check is clear bar spacing. Y'all remember how to do this? So we take 14, subtract 2 covers, subtract 2 ties, subtract 3 longitudinal bars. Why are we subtracting 3 bars? Because 1, 2, 3 along a given row. And divide by 2. Do you all remember that calc? Okay. Now what do we get for this? Say it again. 4. 4 inches. Is that a usable answer? Is that a good answer? Yeah, because, you know, it's got to be less than 6. So after those checks, we can safely say that is our answer. Yeah, unless, you know, it's stated otherwise. But generally, yeah, I want to see the drawing. Because that's the answer. The design, that's the answer. Does that make sense? Any questions on that?
Whenever we put this longitudinal rebar in, we only want it around the edge. What if we estimate like the middle?
Say it again.
Whenever we put the longitudinal rebar in, we just want it around the edge where it's going to be connected to the tie.
But not in the corners. Is that what you're saying?
Not in the middle.
You can put bars in the middle, but you've got to tie it to something. Like typically what's done is if you've got, let's say you got a column, right? And you've got, you know, that, but you have, you know, like a bar right there, then you've got to have another tie in addition to those. You know what I mean? Because it can't, it's got to sit there, so. It doesn't. I mean, the calcs don't change. It's just your clear bar spacing will be a little different because you're looking along, you know, like a given length as opposed to the whole thing. But I would typically avoid that because I think in most cases you should be able to get around that with just using maybe a larger bar and less of them.
What if there's just one bar?
What?
There's just one bar. It sounds like this is kind of way stupid, but I don't know. Mr. Upton was talking about how like flood mounts in beam foundations, if there's some type of concrete beam foundation, they can put one bar in it.
Well, that's a foundation. I mean, a foundation, if we're talking about a pile, it's also laterally confined all the way around. I mean, it's a different animal altogether. You see what I mean? we're talking about a freestanding column. We're talking about,
So you never put a point bar in a freestanding column?
no. No. Well, then just use a steel column. I mean, the W14 by 800. It'll work, I promise. Okay. Does this make sense? Everybody good with this? Okay. I do want to at least get the next example started. This example is pretty straightforward, only it's a circle. Okay. The design expressions don't change, but you just got to make sure that you're doing your math appropriately and going at it. We have a round spiral column to support an axial dead load of 240 and an axial live load of 300. So a couple things. What two values right off the bat changed from the previous example to this one? Phi and alpha. They're different, right? I mean, the load changed, obviously, but I'm talking about just from a design conceptual standpoint. So, but everybody saw that too. We're still going to start with the same assumption for material and all that, so let's just sort of go to work. 73 pages of calcs. Whew. What is this, 19B? Yeah. And what was the dead load? And the live load was 300, right? There you go. They're learning. See, that's the thing. If I make a mistake and you correct me, it must have been that you learned something.
If we make a mistake and you correct us, you're just doing your job.
But when you're correcting me, that means you learned the concept.
That's probably true. We're doing your job.
Either way.
See, and I've done that by design in some things. Like I'll write something and say, is that right? And you go, no, you got to throw the unit conversion. It's like, man, now they're getting it.
No, professors only do that when they, make a mistake and they don't want to admit they made the mistake.
Oh, I'm thinking about the final. Ooh. I'm thinking about some curveballs I could throw out there.
You make two tests, one for people who need curveballs and one for the straight.
So you want a curveball, right?
Yes.
So what do we got for this? You all can plug and chug and tell me what you get. $768. Do I have a second on that? All right. Excuse me. So what is phi and alpha? Okay. Now, so for the column, again, the equations, they don't change. Bless you. It's still, hold on. Phi alpha. Is that not a subscript? Yeah. I was, sort of self-conscious about my handwriting. Everybody just had to point it out. But that's okay. That's all right. So one thing I want to point out right here, okay? So phi is 0.75, alpha is 0.85. When you do the multiplication in brackets, you're going to have a 0.85 again. Don't let that freak you out. That's supposed to be there. Oh, plug jug. And then instead of 1 minus rho, I'll just put the 0.98. And then 768 kips. All right. So is everybody okay with that, the 0.98? What's it?
My number seems wrong, but then we're doing the area.
Yeah. That'd be a big column. So anybody, do you have a number for this? Do I have a second on that? Okay. Now, so that means we do this, right?
No.
Oh, there we go. There we go. So actually, instead of B, I'll use the diameter. I propose that we compute the minimum diameter by saying 4 AG min divided by pi square root. What the? Okay. Let's focus on the column.
18.40 inches.
Say it again. 18.40 inches. Okay. Do I have a second on that? Here's what I'm going to do. I'm going to round down, and I'm going to use 18. Yeah. So what is the actual area of the column going to be? Sound good? Now, let's then calculate the required area of steel, or AST min. So PU divide or minus phi alpha 0.85 FC prime AG divided by phi alpha Fy minus 0.85 FC prime.
So we don't have to put the area minimum requirements since we changed the diameter. Like we do that calculation to figure out what our diameter or base.
Should be around, yeah. Again, where we're using this value to solve for the required amount of steel. So that's why that's valid. You see what I mean? If you took this and multiplied it by 0.02, that would not be accurate. So watch this, 0.75, 0.85, 0.85 again. That's okay. Minus 0.85. Now what do we get? Even? 5.997. I'm going to say use 6 number 9s. What? What's the area of a number 9?
So this time, I'm gonna, like, you said AST before, you said AST required, is that like a difference?
Nah, that doesn't matter. If you want me to be consistent, I can put required here. If I can. That doesn't really matter. Now, is 6 bars feasible? How many bars must we provide for a circular column? What's the minimum limit? For a square column, it's 4. For a circular column, I don't know. You tell me. I do know, but there we go. So a square column must have at least 4 bars. A circular column must have at least 6 bars. So that's a feasible solution. So I propose, now we're not done because we need to do spiral reinforcement. We'll do that next time. But I propose that for this column, use an 18-inch diameter column with 6 number 9s. This isn't that hard, is it? I mean, it's pretty straightforward. What? Pretty much. So I would not wait till the last minute on your homework. Okay, real quick before you go, that's all I have, but don't forget your course evals. Again, I mean, they're free points. Just email me a screen capture or something. That's all I got.